Okay, so I don't think a lot of people are going to join today's session, but I will discuss week 5 and week 6 if whoever has joined, if you all want to continue with the session. Okay, so you can check on your portal. The problems should be released for weeks 5 and 6. There are 3 problems in each of the weeks. Is it visible to you?
Yes, ma'am. They are visible. Those live session questions, right?
Yeah, live coding session.
Mm-hmm.
Okay. Wait, I'll share my screen.
Uh, Ma'am, one thing is that means I have gone through the lectures and everything,
Hmm.
but the way they have coded it, even in the GitHub repo, it feels a little bit hard to digest
Hmm.
actually. So, means can you go with means like I have seen that some simpler approaches are also there. So can we do it using that?
Yeah, see, so the codes that I'm going to write today, I will try my best capacity to explain. You
Hmm.
let me know wherever you face an issue, okay? But I hope the algorithms are clear to you. Kruskal's algorithm, Dijkstra, all of
Yes,
these are clear,
yes, ma'am.
right? Okay, so these are greedy approaches, right? So it's
Mhm.
not very complicated. We just first we have to understand what we are trying to achieve, then we will write the code.
The main problem that I face is basically the mapping part.
Hmm.
How they are mapping everything. That is the main thing that I'm not getting.
Okay, let me try and explain, and you let me know wherever it is difficult.
Yeah,
Okay.
sure.
Okay, so this is the first question from week 5. An airline company wants to make airport to connect N cities. Wait, I'll increase the size. Yeah, you can read. The size is big enough on the font.
Yes.
Okay, so we want to make an airport to connect N cities labeled 0 to N minus 1, right, across the country. Now we have to write a function which is called airport, and it takes argument something called distance map. So what is distance map? It is a weighted adjacency list in this format. So distance map, you can say it's a dictionary basically, right? Now each of the keys are what? Source index means each of the keys are nothing but the 0 to n minus 1 cities, the index of each city, right? So for each city, we have in the value part of each key value pair C, we have a list of tuples where each tuple is what? That from this source index, which destination index I can go to and what distance I have to cover, right? That means, for example, if I start with source index 0, right? So this is 0 is going to be one of the source indices in this distance map. So one of the tuples from 0 will be what? 2 comma 50, right? Because from 0 to 2 there is a direct edge with 50 as the distance covered, the weight. Then again there will be one tuple 1 comma 10, again there will be 3 comma 300, right? These are the different tuples. So distance map is clear, right? For every particular node id or index, we will have a list of such tuples at what destination I can go to and what distance it will cost me. So again these are undirected, right? So this tuple exists like for source index 0 I have a tuple 2 comma 50. Again for source index 2 I'll have a tuple 0 comma 50, because this is undirected. Up to this clear, right? Any doubt? Distance map.
Yes.
Okay. Now, okay. So we are trying to do what? We want this function to return the minimum distance of airport network to connect all N cities. So minimum distance we want. So any idea how to approach this type of problem? Minimum distance. That's the keyword.
Ma'am, we can use min heap.
We can use Kruskal. What type of an algorithm is Kruskal? What does it find?
Uh, min
Do we use Kruskal for MSTs?
MCST.
Yes.
What is an MST?
Minimum cost spanning tree.
Hmm.
Okay, yeah, you can tell me. Okay, MCST. So what is the minimum spanning tree basically? If I have n
Minimum.
nodes, what does MST on those n nodes mean?
MST will be, ma'am, the shortest distance starting from the source.
Hmm.
MST is short as distance.
Means
Not
which
distance.
way you can traverse
Means it will cover it
all
minimum
the
distance. It will cover all the weights,
Hmm.
all the vertices.
Okay, can forget about cost for now. For an MST, can I say that it is the minimum number of edges that takes to connect all the nodes,
Hmm.
right? Now the other condition that I'm putting on is that I need minimum cost, in this case distance. So Kruskal can do that for me, right? It is what type of an approach, Kruskal? Is it greedy?
Greedy.
Greedy, right? So here what I am going to approach it is, so I will have this airport as a dapper function and I'll have the Kruskal as a helper function. So Kruskal will basically do the work. Okay. So I am going to try to find that minimum cost spanning tree. That's the answer to my problem, right? I want a minimum cost spanning tree that connects all of the cities and with the minimum distance being covered, right? I want the MCST. So I can get that from Kruskal. So
Yes.
first we have to try to write the helper function, but okay, let me start with the wrapper function, that is your airport. Okay, this is the just the input that is already given. So let me start with the airport function that we're supposed to write. So def airport, what does it take? It takes the distance map. So distance map. Okay, now see in the given part of the this code. One second. Yeah. So in the given part of the suffix code, you can see that we have taken input the size, that is number of cities, edges. We have formed that distance map, and then we have called this airport function with WL, which is this distance map basically. So WL, and we are printing whatever this airport returns. Okay. So airport takes only one argument, the distance map itself. Now in the first line only, let me take a variable r. In this, I will call the helper function, that is Kruskal. So this will basically do all the work. So in Kruskal, we will also pass this same distance map only. Okay, nothing else we need, just the distance map. Now, before I write anything else in this airport function, I will write the Kruskal itself. Now see, if you understand the algorithm, you should get how to write this function yourself also. Okay. In Kruskal, what am I trying to find? I'm trying to find the edges that will make the minimum cost spanning tree, right? I just want the edges. So those edges I can store in a list. Okay.
Yes, ma'am. Inside the Kruskal,
Hmm.
you can make a tuple of edges component and
Correct. I will make tuples for each of the edges and I can store them in a list maybe. I can return that list that these are the edges I need for the MCST. Right. So let's take W list. This is basically the distance map. So first thing I will do is I'll initialize three things: edges, component, and TE. This is tree edges. Okay, MST edges basically. So
but
first one,
T for three edges means like suppose 50 is. Yeah.
tree edge means what? All of the, this is a list. Okay, tree edges is a list that I'm initializing. In this, I will be storing all the edges that are going to be present in the MST. Okay, this TE is the list that I will return to the airport function.
Hmm.
Okay, so first thing I will take is empty list. Edges is an empty list. I'll explain everything. See, then I have a dictionary, which is the component, and then I have another empty list for TE. There's tree edges. Okay, so three of my containers are now initialized. Now, first thing I will do is, see, first I'll write, then you can tell me yourself why I'm doing this. I want minimum cost, right? That means, it isn't it better that I start with the lowest cost edges, right? So
Ma'am,
how
how we
can
are
I?
getting the lowest cost?
Yeah, that's what I'm going to explain. But we need to start with the lowest cost, right?
Hmm.
So it is
Okay.
better that I have my edges all aligned in that ascending order format, in ascending order of
So
distance.
sorting.
Yeah,
First we will
sorting.
sort.
First we will sort. So how we will sort? First we have the distance map. In distance map, The key value pair is index is to list of tuples of destination index and distance, right? So now from that we are going to create this edges list. Okay, now how to do that? So for u in w list dot keys. So what are the keys of w list? That is distance map. What are the keys? The city index, right? 0 to n minus 1 different city indices, those are the keys. Source
Ma'am,
index is
can
nothing
you
but
show
city
that
index.
input. I think input is given, right, in the bottom of the question.
Wait,
It
okay,
will.
here in the sample input. Okay, so here you can okay, the edges are given, but we have to
Mm.
create the distance map from that. Okay, so
Yes.
distance map is already getting created here. All right, so
Okay.
you take the size and the edges as input, and then distance map is created in this already given suffix code. So
Mhm.
after creating, it will look like this. The distance map is a dictionary. Now, what are the keys of the dictionary? That's what I'm asking. The source index,
Source index.
that means 0 to n minus 1 different indices for n different cities. Right?
Yes.
Those are
Yes.
the keys.
Hmm.
So now for each of the key, what I'm doing, see, edges is a list. So edges dot extend. Okay. Now look at this carefully. I'll have a list of what? D comma U comma V. Okay. In this order for every V comma D in W list of U. What does this mean? In W list for each U, what is stored? A list of V comma D tuples, right? That I can go from U to V by crossing D distance. So in
Ma'am, is it
edges,
like the middle part we are accessing using the D?
we are having the
Middle
entire,
node.
see, D means what? In distance map, for every vertex U, what we have is a list of tuples that destination V I can reach from U by crossing distance D. Correct? This I
Okay,
have
you
in
mean
distance map.
like something like this, like from zero, say U is
Yeah,
zero
from 0,
and V is 2. So we
right.
can reach the distance using 50. That is D.
Yeah, so that is there in distance map, right? Like distance
Hmm.
map, source index 0. There will be one such tuple entry 2 comma 50.
Hmm.
Okay. So for every such 2 comma 50 tuple entry for in source index 0, I will create a tuple like this D comma U comma V, where the first element is the distance. So it will be
Okay,
like 50 comma 0 comma 2.
understood. Hmm.
Okay. That is being added in edges. So this thing I will do for every edge that is present in my distance map.
Hmm.
Now, why I am doing this is because I need to sort according to the weights of every edge. So if I have the first element of the tuple as this, then I can directly sort, right? If I have the first
Yes,
element
yes.
as distance, I can directly sort. But one more thing I'll do before sorting is I'll create the components also. See, component is already a dictionary. So component of initially each node will be its own component, right? So component of U is U itself. Okay, now come out of this for each block. And once this edges list is now populated, right, with D comma U comma V such
Hmm.
tuples, now I can sort them. So just do edges dot sort. So
It will
now,
sort on the
right.
first basis, right?
So
Is
now
D.
we have the tuples in ascending order of edge weights. Okay. Next thing is for, now see, this is the main Kruskal part. For D comma U comma V, that is for every such tuple in the edges list, we will check the components of U and V. Okay, that's how we start Kruskal. If component of U is not equal to component of V, that is if these two nodes are in different components, which they are going to be when we start initially, every node is its own component, right? So if this if statement is correct, then we are going to bring them into the same component, right? We are going to do a union of them into the same component. So at that point, you know that this is an edge I want. right? I want this in my MST because these two are separate components. So I need to join them to form the MST. So you will directly add them to TE. So TE dot append. If there are two nodes which are in different components, they have to come together. They have to be joined in order to form MST, right? So TE dot append. Which edge am I appending? U comma V. Now in C variable, you are going to store the component of U. Okay. Now why, how this will help? See, what is the component of U initially? U itself. Correct. Now I want to join this U and V. I want to bring them into a same component. So I will make that component as V. Okay. You can also bring them both into the U component also, but it is better you take the next one. Why, you will see. So we will bring both U and V into the V component. So currently I have the component, initial component of U stored in C. Okay. Now for W in W list dot keys, you are going to check if, so now your job is to check that what all nodes fall in the previous component of U that is stored in C, right? In C, I have stored the previous component of U. I haven't yet joined these U and V into the same component. I have just stored the component of U. Okay. Into the,
Ma'am, here, here you are saying C is equal to component of U. So that means component dictionary, U is the index. I mean, to
key.
say,
It is the key.
it's the key. So
Yeah.
you are saying it contains all the components. So that means the C will be actually a list.
No. See, component dictionary works what way? That for a particular node, which component does it belong to? Right. This is the component dictionary. See, for how are we initializing it? That every node is first its own component.
Hmm.
So the key value pairs are like this, that component like node 0 is to 0, 1 is to 1, 2 is to 2. This is how it is. Okay, initially. Now my job is that when I try to form the MST, the nodes have to come under the same component, right? They have to be connected.
Yes. Okay.
Okay, so every time I find that there are two such components U and V which are in different components. U is in component U, V is in component V. I will try to unite them into the same component. So obviously, if two nodes are in different components and I'm trying to form a spanning tree, then both of them have to come under the same component. That means they have to be joined by an edge. So I
Yes.
can append that edge to my tree edges. That will definitely be an edge of the MST.
Yes. So U and V will be a tuple
Yeah,
when we
a
append.
tuple, which I'm going to add in this tree edges.
Okay.
Okay. Then in C variable, I'm storing the current component of U. Okay. So initially, like what was U's component? U only. Right.
Yes.
Every
Yes.
node was its own component. So use component, whatever the previous component of U was or current component of U is, I will store it in C. Okay, I haven't done the union yet. Both of them are still in different components only. I will
Okay.
do it. Now for that union, see, for W in W list of keys, that means now I'm going through all the nodes one by one. What am I going to check? If for any node, I will check the component of W. For any node, if the component of W is same as that of C, that means they are in the same component as U, right? Then you will update their component. This component of W will be now updated to component of V.
Ma'am, can't we just do this component of W is equal to component of U? It's like why we are storing that
Because see, this is the first initial iteration, but later on when you do next iterations, then there will be a lot of number of
updates
nodes in
will
the
be.
same component, right?
Mhm.
Yeah, so all of them have to be one by one converted into the new component. So we need this for loop.
Okay.
Okay. So now what happened, that everything that is connected to C or U node, basically everything that is connected to U and U itself, all are converted into V component. So now they're all under the same component. Now your UV edge exists in the MST. in the same component. So like this, I will just do it for every d comma u comma v. Right. Every such edge I'm going
Okay.
to check that are
Hmm.
these two in same component. If they're same component, you don't have to do anything else. But if they're different component, you have to add that edge. And also, since we are going to add an edge, that means they are now in the same component. So you have to update the component dictionary also.
Yes.
So this thing will continue for every d comma u comma v edge. Okay. And at the end of it, your TE, that is tree edges, should be now populated with all the distinct edges that I need in my MST.
Yes.
So you will
Obviously.
simply just do return TE. That's it. That's the Kruskal. Now this TE that is returned is what? It is a list of tuples, where each tuple is the edge, a distinct edge in the MST. Okay, so
Hmm.
now that is being stored in R. Okay, now come back to the airport wrapper function. It is now stored in R. Next, what I have to check? I want the minimum cost. Correct. This wants us to return what? Return the minimum distance to connect all n cities. So I have to calculate that distance now. So that is very easy. You just go through all the edges and add the distance. So I will take some variable s equals to 0. Now for e in R. So what is e in R? One such edge, u comma v, one such tuple. For ed, but remember in R we don't have the weights, right? In R we just have the
Yes.
edge, u comma v. So for the weight we need to again go back to the distance map. So for ed in distance map, now where am I going to search? Distance map of what? In E I have two nodes, u comma v. So there is an edge between u and v. In distance map I have an entry for every single source index, right? So I can check for E. I'm sorry, since I have a tuple u comma v, I can check for u. I just have to find the distance between u and v, right? Whether I check it for v to u or u to v doesn't matter, it is undirected.
Yes. Indirected. Huh?
So I can simply write E of 0, that is the U node, right? And I will check that in distance map. So against U node, what is ED? A list of tuples like this, that from U node, what all V nodes I can reach and what are the different distances I have to cover.
Yes. And that is being created in this boilerplate code that was
Yeah,
given
that
to
is
us, right?
already given. Yeah.
Okay. Okay.
So now I just have to access the distance. That means in ED, I have to check where my V matches, right? I need a particular V for a particular UV. Now U2, there are multiple edges going from U, right? From 0, I have 3 edges. From 2 to 2 to 1 to 3. Now let's say my MST edge is 0, comma 2. That means in the distance map, I have to find this edge 0 to 2 and the
Hmm.
distance 50. So for that, I will access if ED of 0. That means see, why 0? Because in every tuple, the first entry is the destination index. So I'm trying to match the destination. If ed0 is equal to e of 1, that is the v, the tree edge v, right? The destination. I'm just trying to match the destination. Wherever the destination matches, just extract the weight and add it. So s plus equal to, where is the weight present? Ed of 0. See,
ADF.
is ed of 1, right? Ed of 0 is destination, ed of 1 is the distance. Ed is one such tuple, destination comma distance. So
Hmm.
just add
Yes.
the distance, ed of 1. So at the end, you will have matched all of the destinations, right? For each u, you have matched all of the v's, and you have added all the edges, edge weights. So now your s variable contains that minimum cost that it will take for us to connect all the cities. So lastly, we just return that, return s. Okay, let me just run this once and see if there is a problem. Something is wrong. Okay, expected output. Where is it filling? Line 37, airport. Okay. Line 21, R Kruskal. No, this is correct only. Okay, let me check.
Ma'am, when you created the tuple there, you added extra comma, I guess, VD comma in W list.
Oh,
Edges.extend
this one.
DUV. There is one that error, and I think one more error will be there. We'll just run once.
Okay, let's see once. Hmm. Okay, that didn't give any change. Okay, so S is 0 for E and R. We are taking distance map E of 0. Okay, ED0 is equal to ED1 plus equal to ED1 return S. Okay, this looks fine only. Maybe there is some problem in the Cruscal. Let me check this once. We have edges component TE for U in W list of keys. Edges dot extend DUV for V comma D in W list of U. Yeah, okay. Then components are initialized, then edges are sorted. Edge dot okay. So for D comma U comma V in edges, components, if they are not matching, then we append it in TE. Okay. And C component is updated for W in W list dot keys. If component is equal to C, then we update it to V component and return TE. No, this is correct only. Where is the error? Let's see. Print airport W list. There is some error here. This is returning the correct thing only. Might be some mistake is there. Distance map R Cruscal. So error is showing in line 37 and this, right?
Line 37 is not there even.
Yeah, it is not there. Okay, and line 21 there is no error. I'm just initializing S. This code should work. Should I try it in Spider once and check? Maybe we could do that. But it should work. Why it's not working here? Actual output test. Print this. So once it comes here, calls the airport function, then it calls the Cruscal with distance map. Yeah, everything is correct only. Okay, let me just try this in Spider once, right? And then we can give the input also from here and see if it works. So we know that there is no configuration problem at least. Wait, you can't see the screen. Wait. Alright, let me copy paste this in.
Ma'am, can't we just add distance in a tree edges with a U and V? And in airport, we should write for DUV in R. Then we will just add all the distances.
You're saying that we can just add the distance here only.
No, in top, in TE dot append in ninth line.
Yeah, here you're saying that along with U and V, we should also add the
Yes.
distances.
I had tried and it is giving me correct answer.
Yeah, it will give. Definitely. You can add it here also. Then you can just call it back in airport and you can just add the distances. That is also you can do. But
Yeah.
I'm trying to see what is wrong in this code because this should also work. There
Ma'am,
is
which
nothing.
error is coming?
On Spider.
See this one.
Sending two arguments in
Yes,
append
ma'am.
clause.
Ma'am, here in te.append, add a tuples in UNV, add square brackets. Sorry,
Oh, wait. I
yes,
missed this, right?
They are.
it
There
was
That's
should
also
be one
the
more.
same
Correct.
problem. Yeah.
Yeah, okay. Thanks a lot. I missed that one parenthesis. Okay. So this one, yeah, you can also do that. You
ma'am.
can
One
add.
question I have.
Hmm, hmm.
Means the main problem that I think many of us face is that between the steps, how to visualize the data, what is going on inside it.
See,
So.
first of all, you are not going to start writing the code before you understand what you are trying to achieve or what code you are trying to write, right?
Mhm,
You will only start once it is clear in your head that these are the steps. I'll go one by one. Like he
mhm.
said that when he was writing the code, he already visualized that he is going to have the distance in that same TE three edges list, so that when he comes back to airport, he doesn't have to go to the distance map again and he can directly take it. Right.
Yes.
So it's up to you, whichever way you want to write the code, because there are different ways of writing. You can do whatever feels easy for you. First visualize it, then you start writing. It's not like you will write one step and then think what I'm going to do next.
No, no, I am saying that mid between the date, sometimes it is hard for me to like here
You
I
can
can
do dry runs, you can do some dry runs if that helps.
that is what I'm asking. Through means like debugging are there, no? Debugging steps are
Yeah.
there.
You can do dry runs, that helps.
Okay.
Because these are, see, lot of inputs are there, no? So it will also take some time to do dry runs. So before
Yes.
exam, I'd say you do a lot of it at home so that you are comfortable in OP.
Mhm.
Okay, so second question is, you are given, okay, that one is clear for everyone, right? Previous one. Anyone has a doubt? First problem? Okay, then we'll start with this. Okay, so here we are given a network of n nodes labeled 0 to n minus 1. You are also given travel times, a list of signal travel times in as directed edges. So here the edges are now directed. Travel times I. Okay, so for each travel times I entry, what is the value stored is a triplet ui, comma vi, comma wi, where ui is the source node, vi is the target node, wi is the time it takes for signal to travel from source to target. Okay, so basically wi is the weight. Write a function min transmission time that takes three arguments: the number of nodes, the travel times dictionary itself, and this. One second. Travel times. Yeah, it's a list. And then S, which is the starting point, right? Source node. So this min transmission accepts number of nodes, a list, travel times, and a source node S to send the signal. The function returns the minimum time required for the signal sent by the source node S to be received by all the remaining n minus 1 nodes. If it is possible to obtain a signal for all n minus 1 nodes, then you do this. If it is not possible, that if I send the signal from my current source node, let's say some S, and it is not possible for it to reach every other node, then you just return -1. So this is, I can say this is a single source shortest path problem, right? Can I say that? So can you give me one such algorithm what I can use here?
Ma'am, means I didn't
Digitras.
understand the question.
See, the question is, I will give three inputs like this. Here, see the sample input 4. This is
Hmm.
the number of edge nodes, right? Number
Okay.
of nodes. And this one is travel times. That is, if I am traveling from node 1 to node 0, then it takes a time of 1. Then again, node 1 to node 2 takes a time of 1. Like this. Okay, this list
Okay.
of travel times, and I will be given a source node that you start at this node. My job is that if I start at this node 2 and I want to send the signal to every other node, then what is the minimum required time for every node to receive the signal? If it
One
is
thing here.
possible,
This second two, right?
hmm,
What two represents in the travel time list? Like, does it represents 231?
No, this second 2 is the source node 2, index of the source node.
Okay, it has nothing to do with the earlier list. Okay.
It is node 2. Okay. So my job is what? That if I start at this node, I want the signal to reach all the nodes. So what is the minimum time in which it can do that? If it is possible to do. And if it is not possible to reach all the other nodes from this source node, then you just return negative of 1. Okay. So for this is a single source shortest path problem. So I can use Dijkstra's algorithm. So first, again, two functions I will be writing, the helper and the wrapper. So first, let's write the wrapper function, that is min transmission time. So today's class I have to go a little fast because this is combined session for week 5 and 6. So we have double problems to solve, right? Okay, n comma travel times the list and the source node. Now see, I will have a list, a dictionary called a list. Okay. Now, what am I using this a list for? You'll see. For I in range n. So basically going through all the nodes. So in a list dictionary, I am creating an entry for each node. Okay, the entry is nothing but an empty list. Now next for u comma v comma d in travel times, that is for each such triplet. See, a list of u dot append v comma d. So do you understand what am I doing here? What is a list? So in a list, how many keys are going to be there?
4.
N number of keys. Yeah, if you take the sample input, 4 keys. Okay. Now for each key, what is the value that is stored? The node that I can reach, the destination, and the time required. Right. So if I take this first sample input for node 1, what are the values that are going to be stored in the list?
0, 1
And
and 2, 1.
2, 1. Right, like this. And for the nodes for which I don't have an edge in this travel times list, they will just have empty lists, nothing else.
Ma'am, why it will be 0, 1, 2, 1?
See, here in a list, first I am creating an entry for each of the nodes, right?
Okay.
For each
Empty.
node, the entry is an empty list.
Okay.
Now I will populate it. That is for every u comma v comma d, that is for every triplet, every such tuple in travel times, like this 1 comma 0 comma 1.
Okay. Hmm.
So here u, that is a list of u, that is a list of 1. What am I appending? A tuple v comma d into its list against this. See, like a list of I. Here take this I as 1. In the
Okay.
corresponding list, you will store an entry of the tuple v comma d. So what is v comma d? 0 comma 1. That is, I
Okay.
can reach node 0 in time 1. Again, for 1, I have one more tuple, 2 comma 1. I can reach node 2 in time 1.
And
So
3 comma 1 for 2, right?
yeah, for node 2, I will have 3 comma 1. Now for node 0 and node 3, I don't have any entries. So they will remain empty lists in a list. So a list is such a dictionary that I have created. Okay. Now next I will be calling the helper function. So here now we can just take two variables, distance and infinity. Basically I have to define an infinity. Okay, because we know in Dijkstra, where do we start? Each see, initially I want that from the
All
source I have to reach all the nodes, right? So all the distances initially are going to be what? Infinity.
infinity.
Except the source node. It is going to be 0 because source to source distance is 0. Okay. So from that Dijkstra, I will be getting two things in return. I will have a distance, which is list or dictionary, whatever it is, it will be returned. What is that distance? It is basically the distance from source to every node. That will be calculated in Dijkstra. That will be returned and the infinity will be returned. So two things. So here now I will call Dijkstra.
Ma'am, what will be that infinity?
Yeah, I will do it. I will write what is the infinity once I write the Dijkstra function. Okay. So Dijkstra, let's call Dijkstra list. It will take the A list that I created and the source node. Okay. Now let's write the helper function. So def Dijkstra list. It is taking the W list or A list, whatever you want to call it, and the source node. Now let's define the infinity. So infinity has to be such a value which will be greater than all possible distances from source, right? Infinity has to be such a big value. So let's write it in this way. Infinity I will define as 1 plus, you see this and tell me if it is possible for any distance to be greater than this. Okay, I will take length of W list dot keys.
I generally just take infinity as 99,000.
No, you cannot take any such value, right? We don't know what will be the sample input, so we will take something that is safe, that will always be greater.
Okay.
Okay, so just take length of W list dot keys. Now multiply it with max, max of, see, D for U in W list dot keys for V comma D in W list of U. Now try to understand what this is and if any distance from source to any node can be greater than this. So basically length of keys, that is how many distinct nodes are there, right? And D for U in W list of keys for V comma D in W list of U. So W list of U, for every V comma D, we know that, like for W list of U, if U is 1, there is a tuple like 0 comma 1, there is a tuple like 2 comma 1. So for every such V comma D tuple, we are taking the distance. Understood? We are taking the maximum possible distance and multiplying that with the length, that is number of keys, plus 1. So is it possible to get a distance that is greater than this? See, in this case, what is in, take the first sample input. What is W list dot keys? What is the length of that? 4.
4, huh?
Right. What is the maximum distance from any node to any node? What is the max distance possible?
1.
1.
1.
So 4 into 1 plus 1, that is 5. So from source to any, like this, in this distance that we're calculating, can there be any distance that goes beyond 5?
No.
Not possible. This is the max. So this will be our infinity. Okay, now infinity is defined. Next main thing we are coming to now is two things we need: a visited dictionary and a distance dictionary. Visited will keep track of what all nodes I have visited, what are still not visited, and distance will keep track of distance of each node from source. Okay, so initialize two things: visited and distance.
Distance.
So this is, both are dictionaries. Okay, now see, first we will have every visited, that is in visited, for every node we will have the value false because we haven't visited anything yet. And for distance also, for every node we will have what? Infinity, right? Initially we start with distance infinity. So for V in W list dot keys, that is for every node, we are going to initialize two things: visited V and distance V. Both the dictionaries will have an entry for each node, right? We will initialize them all to, in visited, initialize them to false, the values, and in distance, initialize them to infinity. So initialization is done for every node. Now, for distance, what did I say? Source node, what should be the distance from source to source? What is distance from source to source? 0.
0.
So initialize that to 0. Distance of S is 0. Okay. Now we will do the actual iterations. Okay. So how many iterations are there in Dijkstra? How many times do we relax? As many nodes as there are. Right? How many times do you relax the edges? How many iterations do we do? As many nodes as there are.
N minus 1.
So for you in wlist dot keys, that many iterations I will have. Now in every iteration, see, first let's understand what we are trying to do. I need to find the minimum distance, current minimum distance. Okay. I will store that in a variable called, let's say, next d. So that is the next node that I will traverse to. Next, see, from source, two nodes or more than one node can have minimum distance, right? In that case, I will store them in a list that these are all the possible nodes I can go to next. How will I choose the next node from there? I will use the index. Maybe from source 2, I have two nodes I can go to. Maybe I can go to 3, I can go to 1. Both are at minimum distance. In that case, I will pick 1 because I will now go index wise. Whichever is the smaller index, I will pick that. So I need to first find out what is the minimum distance that I can go to right now. Then I have to find out what are the possible nodes that are at that minimum distance. Okay. Next, I will have to pick a node with that minimum distance. So I will pick the node with the lowest index in case there are multiple choices available. If there is only one choice, you take that. Now we are going to visit this node, which is at a minimum distance. So in visited dictionary, the entry for this node should be turned to true. That is, now I have visited this node. Okay. Up to this, is it clear, the idea?
Ma'am, can you repeat once again?
Look, first thing I will do is I need to find, for every iteration, I need to find what is the first minimum distance available to me right now
Okay.
to travel to any node. So you tell me, in the initialization, in distance dictionary, you can see for every node it is infinity except for which node?
First node, it
Source
is
node.
root node.
For source node, it is 0. That means I will start with this node. Okay.
Okay.
But in future iterations, it might happen that minimum distance, at minimum distance, more than one node is present.
Yes.
In that case, how will I pick? I will pick the node which has the lower index.
Lower index value.
So once I pick the node, I know this is the node I'm going to visit next. So in visited dictionary, I'm going to turn that into true. The entry for that will go from false to true. That is, now this node has been visited.
Okay.
Okay, up to this, let's write the code. So for every iteration, first thing we do is find the minimum distance. So next d will store that minimum distance. So that is minimum of distance v for v in wlist dot keys if the condition is that I haven't visited that node yet for whom I'm taking the distance. Okay, so not visited v. Given that I haven't visited this node v yet, I can take into account its distance, and among all such not visited nodes, I will take the minimum distance that is there. So now my next d is done. Wait, here I think I'm missing one bracket somewhere. Yeah, here I have to open it. This is a list. Now I have the minimum distance. Now next I have to find that who are the nodes who are present at this minimum distance. So next v list, let's call it. This is a list. There can be more than one such nodes present at the minimum distance. So who are those nodes? V for v in wlist dot keys. What is the condition? If I haven't visited it already. So if not visited v, that is visited v is false, not of that is true. Another condition is what? And the distance matches the minimum distance. So and distance of v is equal to next d, that is our minimum distance. So this is a list of all nodes who are present at the minimum distance currently. Now I will pick the node with the minimum index. So call that node next v, which is going to be, this is very easy. Tell me minimum of what? Next v list. Whatever is the
Ne-
minimum element.
Next we list, we will take the minimum element from
So
there.
up to now we have understood we are trying to pick the minimum distance element, right? Once we have picked it, we will visit it. So now change the entry in the visited dictionary. So visited of v, or sorry, not v, visited of next v is now set to true. We have visited. Okay, now once I have visited, now what I'll do, see, I'll run a for loop. So for v comma d, that is for every v comma d tuple in w list of next v, that is the node that I have visited currently. In w list there is an entry, right, for every node, which is a list of tuples, destination and time required. So for every such v comma d tuple entry for this current next v that I'm visiting, I will check if that node is visited or not. So if not visited v, this is basically relaxing the edge. Okay, that is I am at this current node next v. Now I know that from next v I can go to this node, right? Every v comma d pair. So I will check that if any of those nodes that I can go to from next v are not visited, then I will try to relax that edge. That is, I will try to make the distance lower, minimum. That is your Dijkstra algorithm, right? You have to relax the edges. So if not visited v, then distance of v will be updated to what? Minimum of current distance v, that is from source to v, whatever is stored in distance dictionary, or distance from source to next v. Tell me the formula you should know. Plus source to next v plus, what is the relaxation formula? Source to
plus
node
D
u
plus
plus
D.
d. Correct. So whatever is the minimum among these two, that will remain. If we see that from source to next v plus d is not a smaller distance than whatever is stored currently in distance dictionary for this node v, then we will not update. But if it is a smaller distance, then you relax the edge, right? Update it. So like this, edge relaxation will happen for every v node that I can reach from next v, right, which is not yet visited. So this entire procedure will repeat how many times? As many nodes as there are. So for loop will iterate 4 times in case of the sample input 1, right? Now once this is done 4 times, all the edges are relaxed, right? Now the distance dictionary has also been updated. I have visited all the nodes, right? Because see, every time I visit a new next v, it is set to true in visited dictionary. And distance is also updated in distance v. Here the distance is being updated, distance dictionary. Every time I relax an edge, the minimum distance is updated in distance dictionary. So both my dictionaries are now updated. So at the end of all 4 iterations, if I'm taking sample input 1, at the end of all 4 iterations, my both dictionaries are now updated, all nodes visited and distance also updated with minimum distance to reach each of the nodes, right? Yes or no? Is it clear? Any doubt?
I'm not understanding actually.
Okay, which part, from which part did you lose it? Here line 12, up to line 12 you understood.
Basically, after everything, after for till next v list, we are taking the not visited list up to that. Yes.
Yeah, okay, so you understood that how am I picking the next node that I'm going to visit, right? If I have more than one options, I'm picking the one with the lowest index. So that is this minimum next v list.
Yes. Yes.
This.
Okay.
So once I visit that, I will set it to true in visited dictionary. The entry will
Yes.
change.
Okay. Hmm.
Okay. Now from this next v node, I can again visit a lot of nodes, right?
Yes,
Where is
obviously.
that stored? So that is stored in our W list, where I have for each node I have an entry stored that these are the v comma d tuples,
Mhm.
v nodes that I can reach using d distance. So now from
Okay, that
next
was
v,
given to us, huh?
yeah, that we created. No, here we created a list. This
Hmm.
is the W list. So now
Okay.
we are checking that from my current next v, what all nodes I can go to, and if they are not visited, then I will try to visit them. Okay. So if I haven't visited, then before visiting those nodes, like from next v, let's say I can go to v1, v2, v3. So I
Hmm.
am checking that what is the current distance. So if I'm trying to go from next v to v1 and v1 is not visited yet, so now I am checking, can I relax this edge from next v to v? Can I lower the distance? So whichever is the lower distance, I will keep that. So in distance dictionary, we have an entry for every node,
Yes.
right?
Okay.
So whatever that distance is, I'll take that into account. So distance of v, and whatever my current distance is from next v to v, that I will take into account. That is distance of next v, that is reaching from source to next v. That is the current node I am at.
What
Plus
distance
d.
next we will give distance?
Distance of next v will give you the distance to reach next v from source.
Okay.
Source to next v, and then from there plus d is the distance that it takes to reach this
Are we
v1.
comparing here like whether the
We are
previous
trying to
one
find the
was?
minimum one. In Dijkstra, we do this only, that we start with infinity and then we update the edges, the distances, whatever
No,
is the minimum
no, no.
distance.
I'm asking the distance v. Are we trying to compare whichever is the lower distance? We will take that. Either we will keep the current one, that is distance of v,
Yes.
or we
Otherwise,
are
we
trying
will go from source to next v plus d. If that is the minimum one, then we'll take that.
okay.
Whichever
No,
is the minimum, you relax.
no, understood.
Okay. So at the end of this procedure, both my distance and visited dictionaries are now updated, right? Distance dictionary now has all the minimum distances for every node, and visited also is set to true or false according to whatever nodes I have visited, right? If I have visited all nodes, then visited should be true for every node. So after this is done, what all do I need to return? I just need to return the distance dictionary and the infinity value. So just
So
return.
infinity will be updated now.
No, infinity will remain whatever it is. See, this is infinity, the one
Mhm.
that I created here. So just you send these two values back to the uh, wrapper function. So distance comma infinity. This goes back to the wrapper function here. Come to line 24. This dist comma inf. Here this is coming back. Up to this, is it clear? The Dijkstra algorithm itself is clear. Okay.
Ma'am, one thing here, it's like for the minimum value that we were assigning, right?
Hmm.
So we used 1 plus length of. Can we use np.nan or np.inf?
Mm, wait, where do you want to do that?
Infinity?
I haven't done. Maybe you could. I think you can. But
Okay.
this is the safer option.
It is dynamic, right? Means
This is
whatever input says, it will automatically.
exactly. This is dynamic. So it will depend on, like, it will work for any input, right?
Mhm.
Okay. So once you get this back, now what is my job? I have the distance dictionary, that is from source to reaching each node. I have the minimum distance saved in the distance dictionary, and I have the infinity value. Now, what is this asking me to return? That you return what? Minimum time required for signal to be sent from source node to all other nodes, to be received by all other nodes. And if it is not possible to reach all other nodes, then return -1. So now we just have to write this logic. What is that minimum time? So let me have a variable called max time, which I will initialize as 0. Okay, this will store the time. So let's take item for node comma distance in this distance dictionary. So distance dot items. You can itemize like this, so you know this, right? So in
Mhm.
distance dictionary, I have what? Key value pairs are what? Node ID is to the distance that it takes to reach the minimum distance from source to that node. Okay, so I'm taking each such node and distance, and I'm checking that if distance is greater than equal to max time. See, what is the logic? If I have four nodes, okay, now in distance dictionary, I have the distance from source to each node stored. So whatever is the highest distance, that is the time it will take, right? Let's say in distance dictionary there are four entries in sample input one. Let's say from 0, like to reach the source node. Here source node is 2, right? So from source node to 0, let's say it takes some time. Then from source node to 1 it takes some time, source node to 2 it takes some time, 2 to 2 it is 0 always, and source node to 3 it takes some time. So out of these distances or these timings, whatever is the max time, that is the time that I should return, right? Because within that time all the nodes will be reached. The maximum time, within that all nodes will be reached from source node, if it is possible to reach all nodes. Wait, maybe I should write it. Okay, can you see the PDF? PDF you can see?
Yes, ma'am.
This is my distance dictionary. Okay, so I have four nodes: 0, 1, 2, 3. These are what? Distances or time required to reach each of the nodes from the source node. The minimum time required. Correct? So let's say the minimum time required, if source node is 2, minimum time required to reach 0 from 2 is n1. Minimum time required to reach 1 from 2 is n2. Minimum time required to reach 2 from 2 is always 0 because it is the source node. And minimum time required to reach 3 from 2 is n3. So among n1, n2, n3, whatever is the highest one, let's say n1 is 4, n2 is 6, n3 is 8. So the highest time is 8. So within, if it is in seconds, let's say, then within 8 seconds, if I say, will I not be able to visit all nodes? Signal will reach all nodes. Within 4 seconds, it will reach 0. Within 6 seconds, it will reach 1. Within 8 seconds, it will reach 3. So all nodes it reaches. So I need that maximum time or maximum distance, right? So that is what I'm trying to get here in max time. Understood the logic?
So first one is node, second one is distance, and max time is 0. So you will just update if distance is greater
Yeah,
than
if
max
it is
time.
greater, I'll just update. So max time will be equal to distance. Okay. Now, one more thing. Now, let's say if it is not possible to reach all the nodes. In that case, okay, let's take an example again. Here, let's say to reach node 1 from node 2, it is not possible to reach, so that what is the initialization that I had? For distance dictionary, what was the initialization? Infinity.
Infinity.
So it will remain infinity. In that case, what will be the max time? Infinity itself. Right?
It will never reach. That is the thing, right?
Yeah, but I am still checking. I don't know whether it can reach or not. So I am still checking with all the distances, and it will obviously take the maximum one, which is infinity. So now that is the way to identify whether I can reach all nodes or not, because it should always be less than infinity. So next I will check if, okay, come out of the for loop. Max time, now you got max time. Now I have to check if max time is greater than or equal to infinity. Then I can definitely tell that I am not able to reach all nodes. Signal is not able to reach every node. Correct. So I will return what? -1. I am not able to reach. Else, what will I return? The time required, which is to reach all nodes, which is max time. That's it. The last part of the logic, is it clear? See, I am first trying to find the maximum time it will take to reach the farthest node, let's say. That is from the source node, what is the maximum time it reaches to take a node? So within that time, obviously it will have reached all other nodes. Now, if that max time is greater than equal to infinity, that means one of the nodes we were not able to reach, at least one of the nodes. That's why the time remained infinity. So in that case, you will return -1 since it's given in the question. If it is impossible to obtain a signal for all n-1 nodes, return -1. But if I am able to reach all nodes, then max time will definitely be less than infinity. In that case, you just return whatever is the current max time. In our example, I gave you 8 seconds. That could be the max time. Let's run it once. Again, some syntax error might be there. Okay, no, this is running. Okay, so this, tell me first, is the Dijkstra algorithm clear? How to relax the edges? See, as many nodes as you have, that many iterations. For every next v, you are going to relax the edges that are not yet, relax the nodes that are not yet visited. What are the distances? You will compare what is current distance, what is the possible distance, whichever is the minimum one, you take that. Once Dijkstra is done, you return the distance dictionary and the infinity value that you created here. Then the rest of the work is just to find the maximum time, right? So whichever node it takes longest to reach from source node, that is the max time. Within that, all nodes should have been reached. And if you see that max time is greater than equal to infinity, it automatically means that some node wasn't reached. That's why the time remained infinity. In that case, return -1, otherwise return max time. Is it a little bit clear? Okay, you have all gone silent. I'm thinking, I think nobody understood. Okay, tell me, where are you not getting? I mean, just tell me what is the difficulty, in which part? Okay, if you don't tell me, then I'll just go for the next problem then. But yeah, if you want, you can take these codes from me, go through it again by yourself, and then you can ask me if you have any queries.
Where to get these codes? Basically, 9 and 10, right? These two still I'm a little bit confused. I think I have
Which
to
part?
manually
These
do
two
these.
lines, these like next D and next V list. See, I will try to explain it one more time. Next D is what I am trying to find the current minimum distance. Okay. Current minimum distance means where can I reach by the minimum distance possible. So for first iteration, that is always the source node because every other distance is infinity. Right. So how do I find this minimum distance? That means I have to compare the distance of every node, right? That is every entry of the distance dictionary. From there, I'll take the minimum one. That's what I'm doing. Distance v for every v in W list of keys. As long as that node hasn't been visited yet. We will visit
One
each node only once.
wlist.keys, if I'm not wrong, that is the adjacency list that we right now have.
Yes, yes.
And
A list
each key in that is a node.
is a node, correct?
Okay. Now, distance of V is actually checking if that particular, whichever node it is taking, that node
What is
distance,
the distance it will take to reach that node from source node?
if not visited V, means like
If not,
it
if
is not
that node is
visited.
already visited, yeah, that is visited v is false. We haven't visited yet.
Okay.
So like this, you take all the distances and take the minimum one. That is, out of all the not visited nodes, you take the minimum distance one.
Okay, okay. So it is just a list comprehension. Okay.
Yeah, that's
Now,
it. So that
next,
is being stored in next D. Now there might be more than one such nodes present at that minimum distance.
okay.
Right. So v for v in W list of keys, that is for every such every node in W list dot keys, we are checking that if that node is not visited and the distance is equal to next D, that is it is present at the minimum distance. So we will take all of those nodes into a list.
So
Every
next
node.
D is the minimum distance, and now we are
Next D is
taking
the
the
minimum
distance
distance. Yeah.
of the current index, whichever it is they are using the distance
In next V
list.
list, we are trying to find all the nodes which are present at the minimum distance next D and which are not visited yet.
Okay.
Okay. Now among these, I need to find one which I'll visit next, which is next V. What is that? If you have options, then you take the one with the lowest index. So minimum of next V list. Now you visit that node. So visited is set to true for that node next v.
Yes.
Now from this node, what all nodes I can visit? And can I relax any of the edges? That's what I'm doing in line 13 to 16.
Okay.
13 to 15.
Okay.
So if the source to v distance that is already in the distance dictionary, if that is the minimum one, you keep it. And if source to next v plus d is the minimum one, then you keep that. Whatever is minimum.
And that part is clear, ma'am. Just the next D and next V list. It
Yeah.
was not clear, but now I think I am understanding.
Just write it once yourself. Okay. Then
I
it
have
will be
to do
clear.
it myself. I generally do the print statement and check what is the current
Hmm. Yeah.
state of the data that we have, right?
Right. That is
So
a good
that
idea.
way it helps me to visualize things a lot faster. So
Hmm.
that is what is missing. So that's why I'm not able to understand you.
Right. So that you do in an ID, separate ID, and you can check the print statement and see.
I do it that only. Yes. Okay.
Okay. So I hope this is clear. Okay. Now let's go for the last problem of week 5. I don't know how much week 6 I'll be able to cover. At least one or two problems I'll try to do.
Don't we have a session for week 6?
No, no. After this, week 7 starts. So that's why weeks 5 and 6 are combined session. We missed one session last week now because of that quiz one you had,
Quiz one.
revision session.
Yes, yes.
That was supposed to be week 5.
I'm always after the quiz when we not getting a time for week 5 and week 6.
Yeah, yeah. Every time this
Yes,
happens
yes,
only.
always.
Okay, let's see. Okay, this one, see. This should be much easier for you to understand, okay? Because here mainly all of the code is already written. We just have to write a very small function. So here an airlines company has flights operational in n cities labeled 0 to n minus 1. So we have to write a function called best fare, which takes flight route, that is this dictionary which is given, okay, that is from source, same thing, source distance to destination and price, that is destination and cost, that v comma d tuple, in which, and you also take the source node, the destination node, and k. So in which you are given a weighted adjacency list flight route like this. You are also given three integers, source distance and k, which is a positive integer. The function returns the minimum cost and the flight route. In what format? Minimum cost, then the route itself in the form of a list, which is source, then next stop, up to destination. This is your return. This is what your function should return. From source to destination with at most k stops in between. Okay, at most k stops. Now in this k value, source and destination are not included, just the intermediate stations or intermediate airports, they are called, they are included in that k. Okay, so if I say that my minimum route has 5 uh, different stops, that means k value is 5, means total number of uh, stops is 7 including source and destination. So k is the intermediate stops, right? Not including source destination. So we need to find out what is the minimum cost flight route from source to destination using k stops at max. Is it clear? Question. Flight route is given, source is given, destination is given, k is given. So we have to go from source to destination using at most k stops in between. Source destination not included in k. Okay. So we need to find that route and the minimum cost of that route. If there is no such route, then you return not found. Okay. Look here. What all is given to us? This is just the input, right? The size, how many airports are there, that is how many cities are there, what are the edges, what is source, what is destination, what is k. Then you prepare the w list, that is the flight route, like this, just what we did in the last two questions. Then you are calling the best pair function, so this we will write, but before that, see these: add all path and find all path. These two things are given. So what are these doing and how I can incorporate that into my code, these two helper functions, right? Okay, so first I think we should start with this best pair. I should start writing and then I'll explain that what am I calling. So basically I'll be calling the helper functions only. So let's define it. Def best pair. What does it take? It takes the flight route the source, the destination, and k. That is how many stops in between I can take. Now I will take a variable L in which I will be calling find all path. What does find all path take? W list, that is the flight route basically. And it takes what else? Source, destination, and nothing else, right? Find all path takes just 3 arguments. So what is find all path doing? It has a visited dictionary and all path list. So you have to understand that from source to destination, if I'm using k stops at max in between, there can be multiple paths, right? Yes or no? From source to destination, I can have multiple paths using k stops in between at max k
Yes,
stops.
yes. It is possible.
Possible. So now my job is to find the minimum cost path, right? Among all of those paths, I need the minimum cost path. So first I need all the paths that are available. So that I'm trying to find here. Now all path is a list which will store all the different paths. Visited is a dictionary. So what is happening here for v in w list of keys, that is each of the nodes again, we initially haven't visited anything, so all of them are false, just like the previous question. Initially all visited entries are false. Then you have one more list called path empty, which is empty list. So here I will store the path. Every path that I find I will initially store here and then add it to all path. So then you have this add all path. This function call is here, which takes again w list, that is the flight route, source destination, the visited dictionary, the path list, and the all path list, all of this. So now let's go to the definition of add all path. So what it does is I have the source and the destination, right? So I can set source to true because that is the starting point. Just like in previous one, we said visited of a distance of s to 0. Source node, I will visit first. So first I will turn that into true. Visited of u is true.
Hmm.
Now that is the first node in my path. So path dot append u. Right, I am forming a path.
Hmm.
So in my list, path list, now I have u, first node. If u and d are same, that is source is the destination, in that case just create a copy of this path and add it to all path. Okay,
So what
which
will be the L? Will it be entire
it is
list?
just it is just a copy of this path list. Okay,
Okay.
I am appending to all path. I'm just creating a copy. I'm not disturbing the original path. That's it.
Mhm.
This is the base condition. This is the stopping criteria, that when I've reached destination I will stop. Okay, else, that is obviously my source and destination are different. Let's see if they have a test case given here. I think they have. Yeah, here you see I have 5 vertices. What is the source? Source is 0, destination is 4. So in that case 0 is added to path, right? But 0 is not equal to 4. So come to the else part. Here for I in w list of u, what is u? 0 in my example. What is I? Each such pair, that is 0 to destination and cost. That is here the pairs will be like this. 0 for 0 I'll have 1 comma 1000, 2 comma 500, 3 comma 3000, right? These are all the destinations I can reach from 0. So for each such tuple you check if visited of I of 0 is false, that is if the destination has not been visited yet. Tell me in this tuple 1 comma 1000, what is I of 0?
0.
In the tuple 1 comma 1000,
Okay, 1 comma 1000. 1.
1 is I of 0. So I'll check if it's 1 visited. If it is not, then visited of I of 0 will be false, right? Then I will check if I can
No,
take
one
this path,
second. This I of 0, right?
I of 0.
So I is W list of U. So that means I will be every tuple, right?
Every tuple I can reach from 0. That is that tuple, like v comma distance for every u comma v pair.
Okay. Now you are saying that in 1 comma 1000, but here in the tuple it says 0 1000, right?
No,
So
no,
the first element should be
no,
0,
no,
right?
no. That is not the tuple. We created the w list, right? This is the edges. We created w list just like this flight route that we create. We are doing for
Okay.
this for the last 2 problems also, right? We have a source
Hmm.
index destination and price, this tuple, destination comma price.
Yes, yes, yes.
So for 0, what are those tuples? 1 comma 1000 is such a
One.
tuple, 2
Uh-huh.
comma 500, 3 comma 3000.
Okay,
So
okay.
each of these tuples I'm checking. So
Okay.
here I means 1 comma 1000.
Mhm.
So I of 0 is 1. So I am checking, have I visited I? If I have not, then visited of I of 0 should be false. This
Yes.
line, right? Then I will check that now can I take this path? So I will again call the same function add all path with source node is now I of 0. Destination is same.
Okay.
So I am now advancing to the next node in my path. Now again you check. See, now I'm visiting I of 0. That is, let's take 1 in this case. Okay, if I take 1. Now 1 will be set to true. Visited of 1 is true. Again you append that to the path, current path. Right? So now your path is 0 comma 1. Or in this case it is, I mean, the path has been sent from here only, right? So path will not be reinitialized. It is that same path. So 0 comma 1. Now you again check, have I reached the destination? Yes. Or if it is no, then come to the else part again. See what all nodes I can reach from 1. So from 1, what are the tuples? You can see here 1 comma 3 comma 300. So 3 comma 300 is there. I can reach from 1 to 3. Only one node I can go to. Right. So now I will again come to 3 and check if it is visited. If it is not visited, then again call add all path with 3 as the source. Like this, I need to reach my destination. Understood. So one path, can I say, will be like this: 0 to 1 to 3 to 4. This is one path. If my
Hmm.
source is 0, destination is 4, this is one path. So the path list is being updated. Now in every recursive call, the U is being appended to path. So at one point when you reach 4, you will come to this part. U is equal to D. Right. So now you know that the path has ended. I have reached my destination. So you add a copy of that path to all path. That is, this is one of the paths I can take. Now there will be one more path like this: 0 comma 2 comma 4. There is a path to reach from 0 to 4 by just using the node 2. So among all such paths, you need to find what is the minimum cost path with at most k stops in between. Right. Now you can see that k is not incorporated anywhere here. So that I have to incorporate in my actual best pair function. So I hope the above two
Okay.
functions are clear to you. Find all path and this.
One is adding all the path, and
Yeah,
second
see,
one is.
add all path is basically finding all possible paths. And
Hmm.
find all path is generating that list of every path. That is all
Yes.
path list.
Yes.
That's it. Now, see, find all path I'm calling here in best pair. So L is going to contain what? List of all possible paths from source to destination. Right?
Hmm. Yes.
Okay. Now see, it can be that no such path exists. Right? It can be the case that no such path exists. In
Hmm.
that case, I will check if L is not equal to, first I have to check that L is not empty. That is, some path exists. That is, L is not equal to empty list. At least one path is there. Then only I'll do the rest of the procedure.
Yes.
So now let's generate a cost. That is some very high cost, right? Just like infinity we generated last time. We are going to generate some very high cost so that we can find the minimum one. Right? We have to start from some high value to get minimum. Just like to get maximum, we have to start from 0. So let this cost be something like this. Again, I'm going to create a dynamic value like this. So 1 plus length of flight route dot keys, same way like I did in the previous question, into max of, I'll take the max price obviously, max of D for U in flight route dot keys for every V comma D tuple in flight route of U. Same as that previous infinity one. Okay. If you can do it in a better way, please do. I am just using this. So this is my maximum cost. No cost can exceed this. Right? Okay, wait, I missed the tuple ending here. Let me check once. Hmm. hmm, Okay, so now some max cost is generated. Next is very easy. See, now I'll take a root variable which is an empty list. So this is basically the minimum cost path I'll be storing in this route. Okay, this is the list which will contain the minimum cost path which I have to return. So now I have to go through all the paths that are in my L list, that is all possible paths, and I have to find out which is the minimum cost one. So for path PTH, I'm writing path in L. L is list of all possible paths from source to destination. Okay, regardless of how many intermediate stops are there. So that also I have to incorporate here, that condition. So for a particular path in this L list, I am checking if, so you tell me what is the max length of the path that I can have if I'm saying at most k stops in between.
K minus 1.
Think clearly. I have k stops in between. That is intermediate. I can take up to k stops. Other than that, in the path, source and destination are also there. That means how many stops can I have at most? How many? Uh, what should be the length of the path at most? At most k in between plus 2.
A
One
plus
for
2.
source,
Yeah.
one for destination. So I can either write length of path is less than equal to k plus 2, or I can write length of path
Ma'am,
is
one thing I'm not understanding why you are adding source and destination. You are saying means the
path.
K K node should be in between, right? K
Yeah,
is
but the paths that you already generated
hmm.
there, like here the path contains, the path list contains the source and destination also, right?
Okay, understood.
So
So
that's
we
why.
can't discard that. Okay.
Yeah. So k plus 2 is the length of the path that is acceptable. As long as it is less than k plus 3, it is acceptable.
Okay.
Correct? I can write here less than equal to k plus 2 or less than k plus 3, whatever you want. So now the condition is fulfilled that there are at most k stops in between. Next, I just have to find out what is the minimum cost. So once it is a valid path with at most k stops in between, I will initialize a sum variable, which is s equals to 0. Now you run a for loop for I in range 0 to uh, length of path minus 1, and for j in flight route path of I. First, let me write, then I'll explain. If path of I plus 1, that is the next node in path, is equal to j of 0, then I will add the corresponding price, that is s equals to s plus j of 1. Okay, now understand what I'm doing. For I in range length 0 to length of path minus 1, right? Basically all of the indices. So for j in flight route path of I, first tell me what is flight route path of I. I in range this. So path of I will give what?
From means flight route means basically
Every node in the route.
every node in that particular flight route
That is given by path of I,
hmm.
right? And I am
From
traversing
that
through every node.
particular node, right? The I is the that particular node,
I
like we
is
said.
that particular index of the node,
Mhm.
right?
Yes.
Path is stored in a list. List length will be what? 0 to length of path minus 1.
Yes.
So every index is I and path of I is the node itself.
Yes.
So flight route of path of I will give what? This adjacency list. That is for every index. Now I am able to check what all destination indices I can go from there and the price.
Yes.
So next I'm checking if path of I plus 1, that is I am in the current index, let's say I am at index 2. Some node I am at, let's say this one, 1, I am at node 1.
Mhm.
Okay. Then what is path of I plus 1? The next node in the path. which is 3 in this path, 0, 1, 3, 4. Okay, in this path, 3 is the next node. So path of I plus 1 is 3. If 3 is equal to j of 0, j is what? Every tuple in path of I. That is every destination comma price tuple that I can reach from ith node. Basically, I am just trying to check that from my current path of I node, what all nodes I can reach, right? If they are in my path, understand? See,
Mhm.
I have this path, let's say 0, 1, 3, 4. Okay.
Mhm.
Now, from 0 to 1, I have a path. Okay. Let's say
Yes.
I'm at node 1. What is the next node in the path? 3.
3.
So path of I plus 1 is node 3. Now I am checking, is there an edge present from 1 to 3? Check. Yes, there is an edge. 1, 3, 300. So for some j, that is the 3, 300 tuple, j
Mhm.
of 0 is 3. That is, there is a match, that there exists an edge. That is,
Okay.
the path is possible.
Mhm.
Then I will just add the corresponding price. In this case, 300.
Okay.
That is, from current node to next node, what is the cost that I have to pay to go?
Understood. And this is how we will keep on adding the
Yes,
minimum
all
cost.
of the, yeah. This is how we'll keep on adding the cost. Now, minimum will come next. This is just adding a cost for a particular path. I'm just
Now,
finding the cost.
so this
S will
particular S
contain
is
the,
the list.
S is the cost.
Okay, S is the cost, and now we will add it into the
No, no.
some.
See, what I will do is, now S is generated means once S is generated, it is the particular cost of a path, right?
Hmm.
The entire
Yes.
path.
Hmm.
Now I have to find the minimum path. So many such S will be generated for every path in this all path
Okay.
dictionary, right?
Hmm.
So now my job is to find the minimum one. So come out of the for loop now. If S is less than cost, I just came out of the inner for loop, okay? That is, for
Hmm.
every path I will be doing this comparison. See, this outer for loop is there for path in L. For every path I'm doing this comparison, that the current cost that I've generated, is it lesser than the cost, the ultimate cost that I did here,
Hmm.
the
Hmm. Hmm.
cost. If it is lesser, we want the minimum one. If it is lesser, then you update. That is, cost will become S.
S. Okay.
And we have found, sorry, wait, S, yeah. And we have found minimum means we have to also update the route. The route is what? The current path.
Hmm.
These two are updated. So like this, once you keep on updating, you will find the minimum cost and the route for that particular cost.
Okay.
So this is now generated. Next thing is, now there are again one condition given in the question. See, if such a route exists, and if it doesn't exist, then you have to return not found. That is, no such path exists from source to destination. Okay. Then what you will do? Where is that if condition? This one. That if there were no paths. So here I started because length of L was, that is, L was not empty. Some path was there. So we also have to write the else condition for that, no? See, first here come, after this if, come out of the for loop, this one. Here you will write if route is not empty. That is, we have found a route with k stops in between. At most k stops. We have found such a route. It is not empty. Then directly
Hmm.
here return cost, minimum cost, and the route itself. If
Okay.
you cannot find such a route with at most k stops in between, then there is an else where you will just return not found. So one not found you will return here. Again, if there are no paths at all, that is, the L list, the all path list is empty. In that case also there will be an else. No, then none of this will be performed. You will directly go to the else statement. So else,
Hmm.
again return not found. So two things can happen. First is, there are no paths from source to destination at all. In that case, directly come to this last not found. In second case, that there are paths, but not with at most k intermediate stops. In that case also you have to return not found. And if there is a path with at most k intermediate stops, then you just return the minimum cost and the route. Okay, is the idea clear? Let's try to test run.
Ma'am, have you zoomed the screen?
Yeah. See. Okay, something I have missed, I think. Best fare. Okay. Line 57. Flight route, source, destination, K. Okay. Now this will be hard to find, but let's try what is wrong here. Okay, we have called find all path. We have taken the flight route, the source to the destination. This is fine. Then if L is not empty, in that case we generate the cost. Let's check the cost once. Max of D for U in flight route keys for V comma D every tuple in flight route of U. Okay, this is also fine. Then route is initialized as empty list for path in L. If length of path is less than k plus 3, then S is 0. That means now this path is valid. So S is initialized to 0 for I in range 0 to length of path minus 1. For J in flight route path of I, we are checking if path of I plus 1 is equal to J of 0, then we will add the price. Next we'll come out of it and check that S is less than cost. That is, this is the minimum cost I'm trying to find. So you update cost and you update route. Then come out of that also. That is both the for loops. Yeah, I'm out here. Now if route is not equal to empty list, then return cost and route. Else return not found, and here also return not found. Yeah, looks correct only. Something I must be missing again. Can you see anything? Please check once. Think a fresh pair of eyes will be better. Difficult to find. Wait, there is something given here. Line 24. Find all path. Here have I missed something? Right route I've given, source I've given, destination I've given. But it is also part of this. Flight route is not defined. Okay. Oh, here I've missed an L. Okay. Let's try. Okay, so these are the 3 problems from week 5. We haven't even started week 6 yet. Let's at least try to do 1-2 problems from week 6. So if you want, just ask me for the codes. I'll send it to you on Discourse. Okay. Now we will do a very easy problem, that is heap. So everyone knows heap data structure, I hope. Max heap, mean heap properties, you know. In max heap, tell me what is the one property of max heap. Tell me what is the relationship between parent and children. In max heap, can parent have smaller value than children?
No.
Max heap, no.
No, right? So max heap parent value must be greater than or equal to the children node. Okay, min heap is just the opposite. So we have to write a function called type of heap. Okay, it will take an array A. In heap are stored in memory in the form of array, right? So it will take one such array in the form of a heap as its argument, and it will return max if the input heap is a max heap and min if the input heap is a min heap, and none otherwise. So if it is not a max heap or a min heap, it will return none. So it's very simple. You just have to write 2 function definitions, one for max heap, one for min heap, and another third definition for this type of heap. So here you're taking the input for the list or the array basically, which is the heap, and you're calling the type of heap. So let's define it. Def type of heap. It will take the list A. So it will just compare if min heap of A, that is min heap is the function that I'm going to write next. So if min heap of A is equal to true, then return min, that is A is a min heap. Again another if statement, if max heap of A is equal to true, then return
Max.
max. And if none of them are true, that is if none of these return statements work, then you just have a third return statement here, return none. Okay, now let's write the min and max heap functions. Let's start with min heap. So def min heap takes the list A. We have to check if it is a min heap or not. So first of all, I need to traverse only till the parent and intermediate, basically the intermediate nodes, not the leaf nodes, right? Only I have to travel till that. So what is that range? See, for I in range length of A minus 2 floor division 2 plus 1. This is the range till which I have to travel in the array. Now, do you understand why I have taken this range, or should I explain it? You can take any example. Okay. Just take any heap of any length. So just tell me this. I mean, if you know heap, you should know that if a parent index is I, then what are the child indices? Left and right child. 2i plus 1, 2i plus 2. Right. If parent is present at I, left child will be at 2i plus 1, right child will be at 2i plus 2. Okay. So by this formula, you can find out that what all indices should the parent nodes be present at. We only need the parent nodes, not the leaf nodes. Only nodes which have at least one child. We need to iterate up to those nodes. So this range will give you that till how long in the list the parent nodes are present. In the list, obviously, you can understand the last elements will be the leaf nodes, right? The child which doesn't have another child. So the leaf nodes will be present at the end of the min heap list. So this is that range. So it will help us traverse through the parent nodes. For example, let us take an example. See this one, 1, 2, 3, 4, 5, 6. What is length of A?
6.
6. 6 minus 2 is 4. 4 division 2 is
2.
see. Length of A minus 2 is 2. 2 floor division 2 is 4 floor division 2 is 2 plus 1, that is 3. So I will iterate through which values? 0, 1, 2.
0, 1, 2.
These are your parent nodes. How can I understand? See, if 0 is a parent node, its child indices will be present at what indices? 2i plus 1, which is 2 into 0 plus 1, that is 1, index 1. And 2 into 0 plus 2, that is, okay, let me quickly write and show you once. Otherwise, this will be confusing. 1, 2, 3, 4, 5, 6. Okay. So my loop is running for I in range. Here we have computed that the range comes out to be 3. So I will take value 0, 1 and 2. So when I value is 0, what are the child indices for this node? If this is a parent node, where should its children be stored? 2i
1
plus
and 2.
1, that is 1. Correct, 1 and 2. 2i plus 2, that is 2. Next I value is 1. So if this is the parent node, where should its children be stored? 2i plus 1, that is 3. And 2i plus 2, that is index 4. Again another I value 2. Where should its children be stored? 2i plus 1, that is 5. And 2i plus 2, that is
6.
6. Now check. For node 0, these two indices, are they present in the list? That is index 0. This is index 0, 1, 2, 3, 4, 5. So for index 0, its children, are they out of bound or are they present in the list?
In
Present.
the list.
Again, for index 1, its children 3 and 4 are not out of bound, they are present. For index 2, one child is present, right? Another is not there. My list is not permitting another child. That means it has only one child. That means I can tell that these three are the parent nodes. Because see, when I go to I equals to 3, now my child is at what index? 7, which doesn't exist. And 8, which also doesn't exist. So this is definitely not a parent node. So I am only traversing the parent node 0, 1 and 2. So that's why the range is taken like that. Understood? Okay, now we'll just do the max heap condition. So for max heap, the parent has to be greater than equal to its children, right? Or we can say that it should be greater than its children. So A of I should be greater than A of 2 star I plus 1, that is left child. Or we are going to confirm that the right child is not out of bounds. That is 2 star I plus 2 is not equal to length of A. That is, it is not equal to that length, right? And A of I is greater than its right child as well. That is A of 2 star I plus 2. So are these the heap condition for min heap or not?
Yes.
This is the heap condition for min heap, right? Now are you sure this is heap condition for min heap?
Ma'am, it's for max heap.
It is for max heap. So if this condition is true, then I will return false here. Okay, because this definition of function is for min heap. Where will I return true? If it is not, if this condition is not valid, then you return true. This is the condition for max heap, that parent is greater than both children and the right child is not out of bounds. Okay, this is definition of min heap. Similar way you have to write the definition for max heap. So from here, and let's just change few things. The range remains same, right? Now what will I change? I will now check for min heap. That is, parent is less than this, or this condition remains same. This part will change. Parent is less than right child also. In that case, it will be a min heap. Otherwise, it's a max heap. So that's all you have to do. Let's try. Yeah. So max heap, min heap, as long as you know the definition, this is a very basic program. Does anyone have a doubt here? Okay, then I'll just try to quickly finish one more problem. Third problem I don't think we'll have time, but second one I'll try to complete. See, this is the MST problem again. Okay, so write a function find redundant edges e comma n that accepts an edge list e in increasing order of the edge weight, where all edge weights are distinct and number of vertices n labeled from 0 to n minus 1 in a connected undirected graph. Okay, so we are writing this function find redundant edges. So it will accept what? An edge list in increasing order of edge weights, where all edge weights are distinct and number of vertices n. It is a connected undirected graph, and the function returns what? A list of redundant edges in increasing order of weight, so that by removing these edges, the graph should still remain connected. with the minimum total cost of edges. So basically it is a minimum cost spanning tree problem, right? So we have to try to write the solution code of complexity that is given as this. So first you tell me, what do you think, how should we approach? Notice that selected edge tuples in the output list should be similar to input edge tuples, that is, don't change the uh, way the tuples are stored, right? And here we can find union find data structure. So everyone knows union find? That is the same thing that we will again check, that if two nodes are in separate components, we'll make a union of them into the same component. So see, here in the solution code, some part of it is already given, that is the input part of it. Rest we have to write. So it is a bit of a bigger problem. I will try to write it and I will explain while I write it, okay? Because we don't have much time. You'll tell me wherever you don't understand. See, first I will make a class. Let's call it make. The problem statement is clear, right? We are trying to find MCST. Right, redundant edges, we just need to find that what are the redundant edges while we are trying to form an MST. Okay, so make union find is a class. Now let's define the constructor. So def init self, three things we need: self dot components, because again we need component for each of the nodes, which component they belong to. So that is, this dictionary will store that. We need self dot members, that is each component has what all members. So that will be, one second, this, yeah. So each component has what members, that will be stored here again in the form of a dictionary. Last one is self dot size, that is the size of each component, that is how many members it has. That is also in the form of a dictionary. Okay, this is your constructor. Now we will write some functions. So first function is def make union find. So it will take obviously self and vertices. What is vertices? Okay, maybe I should start with this part, then it will be clearer to you. See, let's define the function that they're telling us to write. So find redundant edges. In this one, we are taking E, that is the list of all edges, like this one given in sample input 0, 1, 10, 1, 2, 20. These are all, see, in increasing order of edge weights, and all edge weights are distinct. So I'm taking that, and the number of vertices, that is n, in this case 4 in the example. Okay, so first we will call this make union find. So what is st now? It is an object of this class, right? Make union find. Now st dot make union find n. So this is the vertices that I am just having here. So let me define it. What does make union find do? It takes the number of vertices, right? Then see, first for vertex in range, we have to go through all the vertices. So for vertex in range vertices, this is the range, self dot components. So basically every vertex is its own component initially, right? That initialization is happening here. Similarly, then every vertex is a component, that means every component member we will also update. So self dot members for every vertex. The member is what? That vertex only. Initially That is how the initialization is done. Every vertex is a separate component. And size of one component is, every component is 1 because every component is containing a single vertex. So self dot size of vertex is 1. This is the initialization part. Okay. Now again come back to this find redundant edges. So once this is done, the initialization is done for all three things: components, members, and size. We will have a redundant list. So this is the list I want to return. This will contain all the redundant edges while we build the minimum cost spanning tree. So for edge in E, what is E? This list of edges that was sent to that was given by the user, right? This edge list. So for each edge, now we are going to use if st.find edge of 0. So now let's write this find. Every time I'm using something, I'm going to write the definition of that function. So now I'm going to write find. So define find. What does find do? It takes again self and vertex. That is, for every vertex, this find does something. It will return the component for that vertex, right? The component to which that vertex belongs. So return self dot components the vertex. That is, which component this vertex belongs to, it will return. So that's what I'm trying to get here. Now come back to this line 20. If we see that for edge of 0, that is this, let's take the first edge 0, node 0 and node 1. So we are trying to check what are their components. So if the component of edge 0 is not equal to st.find edge of 1, if they're in different components, in that case we have to bring them into the same component. So we will write something like st.union, that is, I'm doing a union of these two vertices into the same component. So edge of 0 and edge of 1, I'm bringing them into the same component. So now let's understand what does union function do. Again define it. So def union. So union will take self, u and v. So two vertices, it is uniting them into the same component. So let's initialize the old component and new component. So C of old will contain the component of u, self dot component of u, and C of new. So we are basically changing component of u to component of v while doing the union. So this is containing self dot component of v. Okay, so C of old, C of new. So we will always add the member in the components which have greater size. Now if self dot size of C new, whichever is the greater one, we will change to that component. Whichever is the larger component, we will add to that. If C new size is greater than equal to self dot size C old, that is C new is the greater one, then for every component that is present in C old, we will change it to C new component. That is, we will change all of the C old nodes into the new component C new, because that is the larger component. So for x in self dot members of C old. Members of C old means every node that is present in the C old component, we will update the component. So self dot components x, we will assign what? C new. We will change for every node, we are changing their component to C new. Again, update members also. So members of C new are now being updated. So members of C new will be, sorry, dot append. Just add the new members, right? X. And lastly, also increase the size of that component. So self dot size of C new plus equal to 1. Every time you add a new node, the component size increases by 1. Now, if C old is the larger component, then just do the same for C old. So else, see, the same thing I will just repeat. Let's just copy paste this part. Whichever is the larger component, you add to that component. So in members of C new, now I will do. Just add everything to C old. So change the component to C old, then you update the C old members and update the size of C old as well. So this is done. Now all my function definitions are done. Now come to find redundant edges. So I am checking the union. Okay, so I'm forming the union here. If they're in different components, do a union. If they're in same component, that is else, then that edge is a redundant edge. So add it to redundant list, because if they're in same component and you still add that edge into your MST, it will create a cycle. So add that edge to redundant edge list, and just after that you can come out of the for loop and return the redundant list. Let me just run this once. Okay, something is again there. Okay, find redundant edges is not defined. Redundant edges. Okay, here the E is in capital.
Also, there are two different spelling for component.
Oh, where is it? Where can you see?
Oh,
Okay, here I have given components and I have given component. No?
yeah,
Let's use
it
components.
is in the multiple section,
Yeah.
like in the line number 18.
Let
Okay,
me update.
yeah, you can do that.
Components. Okay, here all we have done.
And the actual definition is also component.
Yeah, okay, let's update that also. Okay. Okay, so basically this is a union find algorithm. Now this takes this time complexity that is given here. Okay, order of E plus V log V. So why this takes this complexity? We don't have time for the third question. What I can do is I can add this to next week if you want, or I will just post the code on Discourse. You go through it once and you can ask me any query you have. Okay, but let me just explain this E log V thing. So what happens here is the initialization step. Okay, for each of the steps, what happens? We have to process all the edges, right? One by one, we have to process all the edges. In union operation, what happens in the code? Union will merge all elements from smaller set to larger set. That is, whatever is the smaller component, all the nodes from that component will get merged to the larger component, right? So this code manually updates the lists, right? We are updating members, we are updating everything. Basically the member is being appended, right? Every time we add a new node, the member is being appended. You can see we are manually doing that. So each merge operation, it is taking what size of order of size of smaller component. Whatever is the size of the smaller component, that is the time complexity it takes to do the merge operation or the union operation, right? Now this attach smaller set to larger set, this rule that we have, it ensures what, that each vertex changes component at most order of log v times. That is, it cannot change components more than that, right? More than log v times it cannot change components, since the size at least doubles each time. So log v, That is the max. So total cost across all unions cannot exceed order of V log V. That is the time complexity. So what happens when we process the edges? We have two find operations order of 1 each. So the possible union takes order of log V, as I told you. It cannot take more than that because every time the size at least doubles. Now total becomes order of E log V. So two things: initialization, that is make union find, this function that we wrote that takes order of V, and the processing of the edges, that is two parts, finding and doing the union, that takes order of E log V. So together it will take order of E plus V log V. Okay, in next class if I have time I'll just write this down and properly explain to you once, but I'll share the code for the next problem on discourse. Okay, I think this was a very long class, so yeah, I will end it here. Thanks for joining, everyone.
Thank you, ma'am.
Thank you.